that's the question is to find the amplitude ratio, right? What the ratio of the amplitude of the conduction current to displacement current? Okay, so this should be a function of time. This should be a function of time, and I free of t is
It would just be that down there, times A, wouldn't it?
yeah, I'm expecting it to be time dependent. So let me see. What I'm telling you here, dB. It should be the electric field in a free space. Right, so IP of T over I free should be equal to epsilon over epsilon naught. And the amplitude for the polar ID
This must be
for the displacement current, the displacement current amplitude yeah, I think it should be like that. I think you should find, so the epsilon, you don't what that I've done there. It should be 81. I don't see any frequency dependence. Okay, yeah, so it's, okay, I will double check this one. Let's pass. I will come to it later. Okay, let's do this example. Yeah, so this one I'm gonna come back and check it. It should be frequency dependent, and also it should be the resistivity dependent. So somewhere I messed up something. So I will come back to that one. Let's do this example. Okay, a perfectly conducting spherical shell of radius A rotates about the z-axis with angular velocity omega in a uniform magnetic field B. Calculate the electromotive force developed between the North Pole and the equator. So what's responsible for this development of an electromotive force or voltage? So you have this sphere, conducting sphere, and the sphere is rotating about the z-axis. Angular frequency omega. So this is rotating with angular frequency omega, and it's a conductor, and you have a magnetic field B equals B naught Z hat. And we want to find the electromotive difference if you get a voltmeter and measure the voltage between the equator and the North Pole, you would measure some volts. So what is responsible for that voltage? So you develop, you get a voltage when the positive charge is moving one direction and the negative charge is moving the other direction. So how does that happen, and what's responsible for that motion of the charges inside the conductor? So if you consider a charge, dq here, for now let's consider the positive charge, at a position at an angle theta with respect to the z-axis, and the radius is a. So this charge is moving in, so when the sphere is spinning, the charge is also moving in the spherical coordinates, moving in one direction, in the field direction. So it has some velocity. Because of that velocity and its charge and the magnetic force, the magnetic field, it would experience a magnetic force. So because of that magnetic force, this positive charge is forced to move in one direction. So in this case, it's going to be forced to move toward the equatorial plane. So if the positive charge moves to the equatorial plane, then the negative charge must move in the reverse direction towards the equator. So as a result, you have a potential difference between the equatorial plane and the North Pole. So first, let's find this force that drives this charge. So to find that force, I must find the velocity of this charge. So the velocity of dq, that's going to be v in spherical coordinate. How can I write it? So the angular speed times its distance from the axis of rotation. So the axis of rotation is this one, right? This is the axis of rotation, so this distance is a sine of theta. So if you multiply the angular speed with that distance, you get the tangential speed. So that's going to be a omega sine of theta, and the direction is in the p direction. And how can I express the magnetic field in spherical coordinates? So B in spherical coordinates is going to be B equals to B naught times what? So you should know that by now. Cosine of theta along what direction? R half. And minus B naught sine of theta along theta half. So it is just a matter of resolving this into two components. So this is Z hat, right? So the unit vector Z hat, when you decompose it into two, you have one component like that, another component like that. So radial and